This morning's bright sunshine is a nice change from last week's gloom that we had at the end of the week. But boy, it's chilly. Temperatures only in the low 30s this morning here in Madison. There's some light snow is suggested here on this surface map from 8 o'clock local time, but I don't see there's any clouds at all around us, so I don't think that's actually true. They're using the radar, and the radar is kind of indicating some light echo in the middle part of the atmosphere, but not reaching the ground. Anyway, what a dramatic weather map from this morning. We have two major low pressure systems, one of them off of maritime Canada, off the northeast coast of the United States. The other one getting itself organized now just to the west of Lake Winnipeg and parts of Manitoba and Alberta. This is a very intense storm that's getting itself put together quickly. It's going to make it windy around here for the next couple of days. And on its western side, this storm will usher quite cold temperatures for us during the day tomorrow and into Wednesday. We'll have a really chilly day tomorrow. High temperature won't even get to 40 tomorrow. Doesn't look like. In our last lecture, we're talking about the winds around cyclones and anticyclones now that we'd learned about the geostrophic wind, the balance between the pressure gradient and the Coriolis force. And then we just went from looking at straight isobars to more circular isobars. And boy, this map makes it clear that that's really the broad characterization of the isobars that show up on a weather map with weather systems of some intensity on it. This set of almost concentric, maybe ellipsoidal isobars on the storm in the eastern United States and Canada. And then this one over southern Canada, just north of North Dakota. Again, more ellipsoidal but close to circular set of isobars, which are the white lines on this map. And we found, by thinking about the geostrophic wind at 4 compass points around a set of circular isobars, for a region of low pressure at the center of such a set of isobars, the circulation in the northern hemisphere has to be counterclockwise. It's inescapable. And we've been seeing this over and over and over again in our satellite movies. I've been telling you we'll get an explanation for it. We finally did on Friday. And then the same is true of this storm over the Maritimes. And then the region of high pressure with high pressure at its center has a flow that is clockwise around it. So that puts us here in Madison in the position to see substantial winds from the southwest today. Southerly winds of any kind, especially southwesterly winds here in our part of the world, tends to warm us up, and we'll see that that's going to be the case. Today we'll warm up rather dramatically. We'll have a beautiful warm afternoon after a chilly start, and that is a function of very strong southwesterly winds, which of course advect warmer air from the south up towards where we are right now. So we should have a really spectacular afternoon, and that's all associated with the conjunction, really, of this anticyclone over Kentucky and Tennessee and the developing cyclone much farther to the north and west over the prairie provinces of Canada. They're combining to give us a really strong southwesterly flow over Madison. So a very dramatic map to see, especially the day after we first unlocked the secret about why the flow around cyclones in the northern hemisphere is counterclockwise near the surface and why it's clockwise near anticyclones in the same location. Here's the temperature map around the country, and you can see we're chilly. We're in the 28 at Marquette, 32 at Green Bay, 36 in Madison. Not wildly warmer to the south and west, but notably so, 10 degrees warmer, and this is all actually getting close to 2 hours or an hour earlier than us too, so the sun has just maybe come up. But anyway, we're going to have a nice warm-up as the winds come from the southwest, from where it's already much warmer, towards where it's currently colder. The only really warm spot in the country is the Florida Peninsula, 75 Miami, 73 at Tampa, 61 even in Jacksonville, which is pretty good. And then chilly in the Pacific Northwest, and that's where our weather system it has just gone by and is getting itself organized. So it's a little bit of a chill up in that region of the country. Because the central part of the United States is dominated by an anticyclone. Remember, it was straddling the Kentucky-Tennessee border. And the two major cyclones, regions of low pressure, were well up in northeastern maritime Canada and well into southern prairie province Canada. The dew points are quite low across the whole country, with the exception of Florida, where 70 at Miami and 70 at Tampa are the current dew points. But look at, even on the Texas Gulf Coast, where last week we had dew points nearly 70 degrees every day, they're in the low to mid 40s. And then even lower in the interior of Texas. So, and this is a function of the nature of the anticyclone that's kind of slid as far south already as Kentucky, Tennessee, and that has really pushed the moist air off the coast, and it's changed the flow. Now, it's going to begin to moisten up as the anticyclone continues to drift to the east, and the clockwise flow around it starts to bring flow up off the Gulf of Mexico. That will moisten the air over the southern Mississippi Valley and the southern plain states by midweek. But this is the day where it's kind of dry in most of those locations. Okay, let's now take a look at our satellite movie across the continental United States and adjacent waters. So here's storm number 1, the one that's now over maritime Canada. And you can see its cloud mass is pretty extensive, especially over the maritime provinces of Canada. But it has a cold frontal cloud band that stretches all the way back to arguably South Texas and even connected to this cloudiness over the Baja of California. So this is a pretty impressive large-scale weather system. And if you look closely, especially here, you can see elements of the cloudiness rotating counterclockwise for reasons which we now completely understand from our lectures, which is really exciting for me that's the case. And then we can see a really interesting clockwise rotating cloud mass, but notice how it dissipates. It doesn't exist through the whole satellite image. Right in here, it's cloudy and turning clockwise slowly, but it's not going to last because, as we'll learn in a couple of weeks, clockwise motions, those associated with anticyclones, especially at levels above the ground, tend to produce subsiding air that sinks. And as the air sinks, it gets warmed by compression, and it's going to have its relative humidity go down. So clouds tend to evaporate away in regions of subsidence. So this is a really nice catching it in the act satellite movie today of a quite rarely observed phenomenon. We're seeing it there. But you can see there's a nice development going on over Alberta and parts of Saskatchewan, and that's in association with the storm that's up there over the prairie provinces of Canada. And it's only, you can see the difference in organization, it's only now getting itself organized. That will be the star of the show by Wednesday, but it's only in its nascent stages now. This one here is kind of later in its life cycle, and so it looks a little bit better put together. But that's the main stories across the continental U.S. this morning and southern Canada. And here is the radar summary that goes along with that. And you can see, since that storm over the eastern part of the United States and the Maritimes is largely over Canada, we don't get too much precipitation echo from it. Just a little bit here across the border from Maine into New Brunswick, but not too much. Here's that light echo that doesn't appear to have anything falling out of the sky with it over the eastern part of our own state that led the Weather Channel to put snow on the map. And in Wisconsin, it's not snowing here. And then a little bit of light, similarly fog maybe echo across parts of Texas and Louisiana. The only place where it's actually precipitating, apparently, is across the eastern part of Montana, the big sky country, big plains of Montana. And that's probably a mix of rain and snow. The stuff to the west almost surely snow. This here probably rain. And then some shower activity south of the Puget Sound area of Washington State and into northern Oregon and Portland. Okay, so that's it. A pretty nice day across the country, weather-free in terms of these kinds of variables. And now, since we know about the geostrophic wind, we'll be incorporating a look at the 500 millibar map just about every day in our weather discussions. And boy, is there a lot more to learn about these maps the more you study this subject. I can only touch the surface of this. But one thing that stands out, hopefully, if you can first identify the boundaries of the United States, you can see the country, the 48 lower states right in there. There's two very sharp, what we're going to call troughs. Troughs in the geopotential height. These black lines are the equivalent of isobars at about 3 miles above the ground. So this is a very sharp trough. This was last night, unfortunately, at midnight. I couldn't get today's map yet. It's not been constructed. This is last night at midnight, a very sharp trough over the Puget Sound, Vancouver Island, and the northeast Pacific Ocean. And you can see that just to the east of it is where that weather system is beginning to develop over southern Canada. There's a good reason for that. We're going to talk about that as the weeks go on. Why do cyclones develop downstream of these sharp troughs? Notice the trough to the east was over Ohio last night at midnight, and we had a weather system over New England, and that's now moved into the maritime provinces. Again, to the east of the upper level trough, exactly as it turns out will be the case when we learn about why. And this morning's anticyclone was sitting over Kentucky and Tennessee border, right about where the cursor is. And last night at midnight, there was a little bit of a ridge in these isobars, these black lines, cutting from central Ontario down to about northeastern Colorado. And it turns out that anticyclones at the surface develop to the east of ridge axes, whether they're very well developed or kind of muted like this one. And there's very good reasons for that. So there's a lot more to learn, and we're going to have some fun learning that as we go. The last thing I'll say about this map is take a look at all of these observed winds. These are all winds from radiosondes, balloons with instrument packages go up twice a day at all these locations across North America. At almost every single spot, you'll notice that the wind direction indicated by these bobs are drawn such that here at Green Bay, the wind is coming from the north-northwest. And so the bob points up to that direction. Notice that at every one of these locations, the wind bob is just about parallel locally to the orientation of the black lines, which are the equivalent isobars. That's true almost everywhere across the continental U.S. Just remarkable, isn't it? And that's because here's one counterexample at St. John. Actually, it's not a counterexample because the wind bob has to be drawn really long. The wind right at that dot is exactly parallel to the isobars, as it turns out. So the winds at this level, 3 miles or so above the ground, are not impeded at all by friction. And so the geostrophic balance that we can imagine between the pressure gradient and the Coriolis force is pretty well respected by the winds at a level 3 miles above the ground. And also the wind speeds. Remember I told you on Friday, these little flags indicate a 50 knot wind, and then every little feather after that is 10 more. So this wind here at Spokane is 95 knots. This one here at Portland or south of Portland is 95 knots. And notice the spacing between the isobars is really intense there. They're close together. Contrast that with this wind over here at Omaha, which is only 40 knots, and the spacing between the isobars is much wider. So the pressure gradient force near Omaha is weaker. Therefore, I don't need as large a Coriolis force to balance it, and I get a weaker geostrophic wind. Whereas at Spokane or near Portland, I have a really strong pressure gradient force, very strong differences in pressure over short distances. That necessitates that I have a large Coriolis force. The only way to balance it, that is, the only way to do that is to have a really strong horizontal motion to the air parcel. That's why I have a strong wind. So it's really fantastic how these things we've learned in class that are theoretical actually show up as real observations in a day-to-day weather map. Picked at random. I mean, this is just today's weather, so it's random in that sense. But I could show you thousands of these in a row, and they'd all have that characteristic, which is quite remarkable. And then finally, let's take a look at our satellite movie over the Pacific. It's kind of a quiescent period over the Pacific Ocean. Hawaii stands out finally because it's got some cloudiness over the state boundary. You can see where it is. So that gives you an idea where you are in the basin. But there's not much going on in the eastern Pacific Basin. Here's a little cyclone, most likely only at upper levels. It's not really doing much in terms of cloudiness through the deep column, but that's a pretty interesting looking storm, nicely developed and so on. And then you can see here's the cloud mass associated with the storm that's currently developing over western Canada. And you might be able to see this popcorn-looking cumulus cloudiness just offshore of Vancouver Island and the Pacific Northwest of our own country. That's indicative of very, very cold temperatures at upper levels. So those are all individual little thunderstorms surrounded by regions of subsidence outside the updraft core. And the consequence is you get a collection of them that looks speckled like that. And it's downstream, and that's going to be where the really cold air is at upper levels. I'll show you in a minute that's true. And then downstream of that cold air at upper levels is the developing cyclone. So where is the cold air? Well, look at this. These red lines on this map are isotherms. And this isotherm right here is the minus 35 degrees Celsius isotherm. The next one is minus 30. So there's air that last night at midnight, right about the time you saw the beginning of that satellite movie, the air well above the surface of the ocean was minus 30 to minus 35 C. The surface water temperature there is about 50 degrees Fahrenheit, which is 10 C. 45 degrees of temperature difference over just about 5.5 kilometers means that the observed lapse rate is something like 8.5 degrees per kilometer, which, if you recall, sits just between the moist and the dry rate. And so this is conditionally unstable. And it turns out over the ocean, if the air parcel's inhabiting the low-level boundary of the ocean, it's going to be pretty close to saturation. And the condition for conditional instability is if the air parcel is saturated and forced to rise, it'll be freely convective. And that's what we're getting here. So all these things we've learned, you can see they have extensions to real observations and describing the real weather. And I think this gets to be a really exciting time in our term.